Question 1. A fixed mass of an ideal monatomic gas undergoes an isothermal change from A to B as shown. Before I go to the rest of the question, a couple of things that jumped out to me here. Fixed mass means that N is constant, the number of moles is constant, and we would expect that with a heat engine. Ideal and monatomic, the fact that they've said that suggests we might be looking at an adiabatic exchange later, and undergoes isothermal. Okay, well, isothermal means the temperature is constant, which means the change in temperature is 0. And if you remember from the first tutorial, the change in internal energy is equal to that formula. So that means that the change in internal energy for that expansion is also 0. So we've got enough of that already. And that's from A to B. We can do delta U equals 0. The temperature at A is 350 Kelvin. An identical mass of the same ideal monatomic gas undergoes an isobaric change from A to C. So we've got one gas going that way, and we've got one gas going that way. They're both exactly the same. That means we can use the ideal gas equation for both gases, and if it's an identical mass of the same ideal monatomic gas, then nR is going to be the same for both gases. That means we can use this expression PV over T is equal to a constant in any of our questions. Calculate the temperature at C. This is an isobaric expansion. We want to know temperature, and we've got a lot of data at A. So P A V A over T A equals PC VC over TC. So TC equals PC, and I'm cross multiplying here, TA over PAVA. Let's plug in all the details. You can see that by plugging in all the details up here, I've been able to cancel a lot of the numbers, and it becomes a very simple ratio question where TC is equal to 4 times 350 and the temperature is 1400 Kelvin. 2. Calculate the change in internal energy for AC. The change in internal energy is equal to 3 over 2 in R delta T. Well, we've got delta T now because we know that the change in temperature is 1400 minus 350. However, what we don't have is this value of nR, but we can find it because we know that PV equals nRT, so PV over T equals nR, and we have all that data. PCVC over TC is equal to 1.14. Now we can finish off this equation here. Delta U equals 3 over 2 times 1.14 times 1400 minus 350, and that gives us a value of 1800 joules. Again, I'm going to pop that on the diagram just to remind us what's going on. 1800 joules. 3. Determine the energy supplied to the gas during the change AC. Well, Q is equal to delta U plus W. We know that delta U is equal to 1800 joules. How can we find out W? Let's have a look at the graph. Well, the work done is equal to the area underneath this graph, and it's also equal to P delta V. And we've got all that data. P delta V equals, we had 4 times 10 to the 5 was pressure. The change in volume was 3 times 10 to the minus 3. So our work done during that point is 1200 joules. So therefore, the energy supplied is 1800 plus 1200, and that is work done by the gas, so it's a positive number. So our energy supplied is 3000 joules. 4. On the graph, draw a line to represent an adiabatic expansion from A to a state of volume 4.0 times 10 to the minus 3. So point D. What the question asked for was an adiabatic expansion from A to a new point D. So the expansion means that the volume increases, and we're going from this point here So how the heck do we know what to draw? Well, we know that this line here is isothermal. So it moves along an isotherm. What we want to do is create an adiabatic expansion. And we know that an adiabatic expansion would go down through an isotherm, meaning that our final point here would be below point B, because that's on one isotherm, and between 0, which takes us to another isotherm. So our adiabatic expansion would go from point A down through an isotherm with a nice curve to point D. And point D can be anywhere between B and 0 on this vertical line here, but it does need to have crossed an isotherm, and that's why I've chosen that point there. And again, if you go back to the question, it does say that point D should be on this volume line. So it should be on the 4 times 10 to the minus 3 vertical line. B1. State the change in entropy of a gas for the adiabatic expansion from A to D. So change in entropy is Q over T. For an adiabatic expansion, adiabatic means there's no exchange of heat or thermal energy between the system and surroundings. That means that Q is equal to 0. And if Q is equal to 0, then the change in entropy is equal to 0. B2. Explain with reference to the concept of disorder why the entropy of a gas is greater at C than at B. Let's have a look at C and B. At point C, we've got a higher temperature than point B, and we've also got a higher pressure than point B. Let's take that information and explain about the entropy. Point C has greater temperature and pressure than point B at the same volume. This suggests there would be a larger number of microstates. S is equal to KB ln of the number of microstates. Therefore, S is larger at point C than point B. Question 2. An ideal nuclear power plant can be modelled as a heat engine that operates between a hot temperature of 612 degrees Celsius and a cold temperature of 349 degrees Celsius. Calculate the Carnot efficiency of the nuclear power plant. Well, the Carnot efficiency is given in your data booklet. It is this equation here, but of course the temperatures have to be in Kelvin. So temperature cold is equal to 349 degrees Celsius, which is equal to 622 degrees Kelvin. And of course that's just me doing this sum here. For hot temperature, we've got 612 degrees Celsius is equal to 885 degrees Kelvin. So 1 minus 622 divided by 885 gives us a value of 0.297. So our efficiency is equal to 29.7%. Can we give it to 3 significant figures? Yes, well, the data is given to 3 significant figures, so our answer is fine to 3 significant figures. B. Explain with a reason why a real nuclear power plant operating between the stated temperatures cannot reach the efficiency calculated in A. As you remember, the Carnot cycle is the most efficient heat engine. So the efficiency calculated in A is the maximum possible efficiency of a heat engine the real engine will waste energy to surroundings, unlike the Carnot engine, which is theoretical. C. The nuclear power plant works at 71% of the Carnot efficiency. The power produced is 1.3 gigawatts. Calculate how much waste thermal energy is released per hour. Okay, the first thing we'll do is work out what the efficiency of the nuclear power plant is. So the efficiency of the nuclear power plant is 71% of the Carnot efficiency. And that gives us a value of 21.1%. Next thing we want to do is work out the total power generated by the power plant. So the total power is equal to 1.33 gigawatts divided by 0.211, which gives us a value of 6.303 gigawatts. Then what we want to do is work out what the wasted power is, because the question does ask for wasted power. So the wasted power is 6.303 minus 1.33, which gives us a value of 4.973 gigawatts. That's what's wasted per second. And we know it's per second because that's power, which is a joules per second. So we want to find it per hour. So we take this value here, 4.973 gigawatts. We multiply it by 60 to make it per minute. Multiply it by another 60 to make it per hour. And that gives us a value of 17902 gigajoules. So our wasted energy, let's put it into a nicer format, is equal to 1.79 times 10 to the 13 joules. D. Discuss the production of waste heat by the power plant with reference to the first law and second law of thermodynamics. Let's look at the first law first. So we're assuming a Carnot engine, and what a Carnot engine PV diagram looks like is two adiabatic processes and two isothermal processes. For adiabatic, we're looking at Q equals 0, and for isothermal, we're looking at the change in temperature equals 0, so the change in internal energy equals 0. The first law is Q equals delta U plus work done. And because we've got these isothermal expansions, we assume that the change in internal energy is 0. So if we take this first law, that means that any net heat in the system is equal to the net work of the system. The result of the first law is it assumes all heat is converted to work. Now we look at the second law. If there's no waste energy, which means delta Q is equal to 0 and Q equals W from the first law, then the entropy of the system would decrease. And we saw that in step 1. System would decrease. The expulsion of waste energy into the cold surroundings increases the net number of microstates and thus increases entropy. I actually feel this question is not a very good question. I don't think the intent of what exactly is wanted is given particularly well. So this is a good answer and it would get you 3 marks, but there could be other ways to answer that too. Question 3. The PV diagram of the Carnot cycle for a monatomic ideal gas is shown. And to remind ourselves, this is an isothermal expansion. Isothermal means there's no change in temperature, which means there's no change in internal energy. And again, this is an isothermal compression. This is adiabatic. Adiabatic means there's no change of heat between the system and surroundings, and this is also adiabatic as well. A. State what is meant by an adiabatic process. There is no exchange of thermal energy between the system and surroundings. B. Identify the 2 isothermal processes. Well, we've already done that. So it's A to B and C to D. C. The system consists of 0.150 moles of a gas initially at A. The pressure at A is 512 kilopascals and the volume is 1.2 times 10 to the minus 3. 1. Determine the temperature of the gas at A. We've got N equals 0.150, P equals 512 times 10 to the 3, and VA is equal to 1.2 times 10 to the minus 3. We're going to use the ideal gas equation to work out what the temperature is, Pb over nR. That's going to give us an answer of 493 Kelvin. C2. The volume at B is 2.3 times 10 to the minus 3. Determine the pressure at B. It's an ideal gas, which means that this expression holds true. We want to find out what VB is, and we know that TA is equal to TB because it's an isothermal expansion. So PB is equal to PAVA over VB. Plug in the numbers and we get the answer of 267 times 10 to the 3 pascals. D. At C, the volume is VC and the temperature is TC. Show that. Okay, well, this is ringing adiabatic alarm bells to me, so let's just check that our process from B to C is adiabatic. B to C, adiabatic. Great. We know that for an adiabatic expansion, we're looking at PbVb 5 over 3 is equal to PcVc 5 over 3. But we don't want to show that. We want to show something in the middle here. We're not looking at PC, but we can find another expression for PC using the ideal gas equation. PC is equal to nRTC over VC. Plug that into here. PbVb 5 over 3 is equal to nRTCVC 5 over 3 over VC, which is the equivalent of 3 over 3, which means that we can change this. So PbVb 5 over 3 is equal to nRTCV2 over 3. Does that match the expression up there? Yes, it does. Can I tell you that this substitution is quite common for you to be able to use that substitution and come up with an expression like that? It will allow you to find the temperature of a gas undergoing an adiabatic expansion or adiabatic compression. 2. The volume at C is 2.9 times 10 to the minus 3. Calculate the temperature at C. We're going to rearrange that expression above. PbVb 5 over 3. (422 Kelvin). Question 4. A heat engine operates on the cycle shown in the pressure volume diagram. The cycle consists of an isothermal expansion AB. Isothermal. I always write down isothermal equals 0, so delta U equals 0. An isovolumetric change at BC. So isovolumetric. Because there's no area underneath that process, then the work done is equal to 0. And an adiabatic compression at CA. Adiabatic, and again when I see the word adiabatic, I'll always write down Q equals 0. The volume at B is double the volume at A. The gas is an ideal monatomic gas. Again, they have to say ideal and monatomic when they're talking about adiabatic expansion. I suspect we might be using this expression again in a moment, but we'll find out. At A, the pressure of the gas is 4 times 10 to the 6, the temperature is 612, and the volume is blah, blah, blah. The work done by the gas during the isothermal expansion is 416 joules. So the work done here is 416 joules. A1. Justify why the thermal energy supplied during the expansion AB is 416 joules. Great, okay. So thermal energy is what? Well, thermal energy is equal to the change in internal energy plus the work done during the expansion. Well, we know because the temperature doesn't change, then the change in internal energy is equal to 0. So Q is equal to 0 plus W, and therefore Q is equal to W, which is 416 joules. Justify why the thermal energy supplied during the expansion is 416 joules. We should probably write something down there. The temperature does not change. Therefore, delta T equals 0. This means change in internal energy equals 0. From first law, Q equals W. A2. Show that the temperature of the gas at C is 386 Kelvin. Let's go to our PV diagram. We want to show that the temperature is 386 Kelvin here. We've got a lot of data for A. We know that the pressure is equal to 4 times 10 to the 6. I can't be bothered putting all the units in, so just bear with me here. 612. And the volume is 1.5 times 10 to the minus 4. We can see that the process from C to A is an adiabatic compression. That means we can use this relationship as expected. And it's also an ideal gas, so we can use this too. Okay, so we want to prove that the temperature at C is 386 Kelvin. The first thing I'm going to do is find out a value for nR. It just makes things a little bit easier. nR is equal to PV over T, and because it's the same ideal gas everywhere, then nR will be the same at all points. So we can use the data at A to find out what nR is. nR is equal to 0.98. Great. Okay, now let's take this expression here. PAVA 5 over 3 equals PCVC 5 over 3. Let's use that to find out what PC is. PC is equal to PAVA 5 over 3 divided by VC 5 over 3. We know that VC is equal to 2 times VA. So PC is equal to PAVA 5 over 3 over 2 to the power 5 over 3 VA 5 over 3. These cancel, and that gives us PA over 2 to the power 5 over 3. And that gives us the pressure at C is equal to 1.26 times 10 to the 6 pascals. And then we can use PV equals nRT to find the temperature at C. And you plug all the numbers in and you get 386. That's quite a long way of doing it. I just wanted to show you it from first principles. There are other ways of doing this question. In fact, there's too many really for me to go through them all. The key here was to understand that you could use this expression for the adiabatic expansion and this expression together to find out what the temperature at C is. If it's taking too long, let me give you an exam tip. It's worth 2 marks and they tell you the answer. So come back to it later. Just use the fact that Tc is equal to 386 Kelvin and move on. Okay? So 3. Show that the thermal energy removed from the gas for the change Bc is approximately 330 joules. Q is equal to delta U plus work done. Change in internal energy is 3 over 2 nR change in temperature plus the work done from B to C. The work done from B to C is equal to 0 because it's an isovolumetric change. So all we need to do is work out what the change in internal energy is, and that will give us the change in thermal energy. The change in temperature is 612 minus 386, which gives us a value of 226. We worked out nR earlier as 0.98. Plug the values in. 3 over 2 times 0.98 times 226 gives us an answer of 332 joules, which is 330 to 2 significant figures. 4. Determine the efficiency of the heat engine. Do you remember in step 1 I said, look, this is a definition of the heat engine, but there's an equation that I derived at the end which said you don't really need to know this equation, but it really speeds up questions. Okay, let's speed up this question. N equals 1 minus Q out over Q in. So it's 1 minus 330 divided by 416, which gives us 0.21. So the efficiency is 21%. How quick was that? That was 2 marks. And this was 2 marks. Look how much work was required for that. And look how much work was required for that. So if you can remember this equation for the efficiency of a heat engine, not the Carnot cycle, but the heat engine, then you'll save yourself lots of time. B. State and explain at which point in the cycle A, B, C, A, the entropy of the gas is at the largest. The entropy is going to be the largest where there's the most amount of microstates. And in my mind, that's where I'm going to say there's a big temperature and there's a bigger pressure. And remember that the expression for entropy using this concept is that. It's also going to be the point where the most amount of heat has been added, because Q over T. So if we go up to the PV diagram, B is at the highest temperature. It doesn't have the highest pressure, but it's got a big volume. It's also had some heat added at that point to increase that temperature. After B, the entropy is going to decrease. And from C to A, because there's no heat added at that adiabatic compression, the entropy is not going to increase at that point. So the highest entropy point is at B. The highest entropy point is B. Question 5. A monatomic ideal gas. Now the fact that they've said monatomic and ideal, again to me says adiabatic. But let's have a look. Is confined to a cylinder with a volume of 2 times 10 to the minus 3 meters cubed. The initial pressure of the gas is 100 kilopascals. The gas undergoes a 3-step cycle. First, I'm going to actually plot this just now. First, the gas pressure increases by a factor of 5 under a constant volume. So it goes from here up there. Then the gas expands adiabatically to its initial pressure. Finally, it's compressed at constant pressure to its initial volume. So the system looks like that. This is adiabatic. What do I always do when I see the words adiabatic? I put down Q equals naught. And I think we're good to go. Show that the volume of the gas at the end of the adiabatic expansion is approximately 5.3 times 10 to the minus 3. So we're going to use this expression here. and we want to find out what V2 is. So V2 is equal to P1 over P2. And we've been given all that data. The only thing you might have missed during this point is the pressure at the top of the adiabatic expansion is 5 times the initial pressure. So it was 5 times kilopascals. So that's why I put 500 in there and 100 down the bottom. So the value of V2 to the power 5 over 3 is equal to 1.587 times 10 to the minus 4. Therefore, the volume of 2 is equal to 5.25 times 10 to the minus 3 meters cubed. B. Using the axes, sketch the 3-step cycle. Well, we know the initial pressure of the gas is 100 kilopascals and its volume was initially at 2 times 10 to the minus 3. So our initial point is here. Then we know it expands under constant volume, so it's going to be a vertical line up to 500 kilopascals. At that point, it expands adiabatically down to the volume we've just calculated below. So it expands adiabatically down to 5.25, just about there, and it expands down, giving the same pressure that I initially started with, so at 100 kilopascals. So at point B, we're going to do a nice adiabatic expansion, a nice smooth curve, all the way down to this initial pressure point here. That's point C. And then at point C, it compressed at constant pressure to its initial volume. A nice straight line back here, like that. C. The initial temperature of the gas is 290 Kelvin. Calculate the temperature of the gas at the start of the adiabatic expansion. So we want to calculate the temperature of the gas at B. We can use this equation here. And we want to find out what TB is. So TB is equal to PbVb TA over PaVa. And we're going to pop all our data into there. And that brings us down to 5 times 290, which gives us a value of 1450 Kelvin. D. Use your sketched graph in B. Identify the feature that shows the net work is done by the gas in this 3-step cycle. The net work by the cycle is the area enclosed by the cycle. Let's write that down. The net work done by the cycle is shown by the area enclosed within the cycle. I think we have to give it a bit more detail. Work done by the engine, and we'll put B to C, is greater than work done on the engine, and that's from C to A. Therefore, net work is done by the system. I think that will give us 2 marks.